So in 2025, if you look at the data, nearly half of all zero-day exploits, they didn't even target user laptops.
Right, or, typical phishing emails.
Exactly. They went straight for the enterprise infrastructure. I mean, we're talking core networking equipment, edge devices, really just the foundational plumbing of the cloud.
And the scariest part is that attackers are increasingly using AI to find those vulnerabilities in literally milliseconds.
Yeah, it's wild, which means the old rules of cloud architecture are just, well, they're completely out the window.
Pretty much.
And if you're building applications right now, especially on Google Cloud Platform, the sheer speed of innovation is, I mean, it's dizzying. It's really easy to feel overwhelmed, but that is exactly what this deep dive is for.
Right. So we are taking a massive step back today. We're unpacking the Google Cloud Platform technology nuggets for the first half of March 2026.
And just to be clear, our mission here isn't to just read off flashy press releases. We want to cut through the hype and focus entirely on you, the practitioner.
Exactly. We're looking at how beginner to intermediate GCP users can actually run these AI workloads efficiently.
Yeah, and securely, and, practically without completely breaking the bank for your engineering department.
Which is a huge concern right now.
Yeah.
So let's start right at the top of the stack, because before we build any of the infrastructure, we really have to look at the models themselves.
Right, how we actually communicate with them. And the source material highlights this new resource. It's called the Ultimate Nano Banana Prompting Guide.
I know, the name is something else.
It's a very quirky name, but it's actually an incredibly dense technical breakdown. It covers model overviews, technical specs, and how everything integrates with Google's creative models.
Yeah, like VO for video generation and Lyria for audio.
Exactly. Plus, it has these highly specific best practices for prompting frameworks. But, the guide quickly pivots to the infrastructure side.
It does, yeah, because it tackles a massive pain point on Vertex AI. And just as a quick reminder, Vertex AI is basically Google's fully managed machine learning platform. It's where you build and deploy and scale your AI models.
Right. And if you're a practitioner on Vertex, your absolute nightmare scenario is hitting that 429 resource exhausted error.
Oh yeah, the dreaded hug of death.
Right. You build this amazing AI feature, your users absolutely love it, they flood the system with requests, and suddenly, bam, everyone hits a brick wall because you exhausted your API quota.
And what the guide points out is that solving that isn't just about, asking for a quota increase. You have to align your consumption model with your actual traffic patterns.
Okay, so how does Google break that down?
Well, there are basically three tiers. First, you have standard pay-as-you-go, which is your baseline. You just pay for the compute resources you actually consume.
Makes sense.
Then there's priority pay-go. This one is built for business-critical workloads that might have unpredictable spikes. So it gives your traffic priority routing when the whole network gets congested.
Okay, and the third one?
The third is provision throughput. And this is a fixed cost subscription that guarantees isolated capacity for your specific workload. So it's for mission-critical, latency-sensitive stuff.
Okay, I think an analogy helps here. So it's kind of like managing a massive theme park, right?
Okay, I'm tracking.
So standard pay-as-you-go is like your general admission ticket. It's perfectly fine on a quiet Tuesday, but on a busy Saturday, you are definitely standing in line.
Right. And priority pay-go would be what, the express pass?
Exactly. You're still sharing the park with everyone else, but you get to jump to the front of the line when things get crazy.
I like that.
And then provision throughput is basically renting out the entire roller coaster for your VIP group. I mean, there is zero wait time guaranteed, but you're paying a huge premium for that exclusivity.
That is exactly what it is. And for some apps, that exclusivity is mandatory. But beyond just buying the right tier, the guide really emphasizes engineering your way out of these bottlenecks.
What kind of engineering?
Things like global model routing, which automatically bounces your user requests across different geographic regions to find available capacity. And then, crucially, context caching.
Okay, let's pause on context caching, because this feels like a massive cost saver, and I want to make sure I understand it. So let's say I upload a giant 100-page financial PDF to an AI model, and I ask it 5 different questions.
Okay, standard use case.
Normally, the model has to process all 100 pages from scratch, 5 separate times, right? And I have to pay for all those redundant tokens every single time.
Exactly. And it takes forever to process.
Mm-hmm.
Context caching essentially stores the mathematical representation of that PDF in the model's short-term memory.
Oh, so it's like a barista who remembers your super complicated coffee order, so you don't have to stand there and repeat the whole thing every single morning.
Yes. That's a perfect way to look at it. You pay a small storage fee for the cache, but you only pay the heavy compute cost to process those tokens once. Yeah, and the model just references the cache for every subsequent question. And the guide also mentions routing simpler tasks to lighter, cheaper models, like using Gemini 2.5 Flashlight just for summarization.
Right, so your cost per query just plummets. But, I mean, even with caching and cheaper models, if we go back to that analogy, renting out the entire roller coaster with provisioned throughput sounds incredibly expensive.
It definitely is.
So if I'm managing an internal development team, how do I actually run these AI models affordably without wasting a bunch of expensive hardware?
Well, this is where we shift over to the compute layer. Google published this distinct guide on how to do affordable AI on GKE.
Okay, and GKE is the Google Kubernetes engine, right? The managed environment for deploying and scaling containerized applications.
Exactly. So they outline this really clever three-part combo to deploy tools like Ollama without wasting hardware. The first piece is GKE Autopilot.
And Autopilot automates the background infrastructure, right? So my developers don't have to manually set up nodes or install complex GPU drivers on a Tuesday morning.
Right, it completely abstracts that away. But the real budget saver is the second part, GPU time sharing.
Okay, what does that mean practically?
Well, an NVIDIA L4 GPU is a physical beast. If you dedicate that whole GPU to one internal app, it's going to sit idle, like most of the time. Time sharing slices it up so multiple applications can use that one physical GPU simultaneously.
But wait, if I have 5 different development teams sharing one physical GPU, aren't they going to step on each other's toes? Like Team A overwrites Team B's dependencies and the whole thing crashes.
They absolutely would.
Yeah.
Which is why the third part of the combo is so important. It's called vCluster. It basically gives different teams private virtual workspaces while still sharing the underlying hardware.
Oh, I see. So it's kind of like having a bunch of roommates sharing a luxury apartment.
Okay, go on now.
Like everyone gets their own private, locked bedroom. That's the vCluster. But they all share the really expensive kitchen appliances like the NVIDIA L4 GPU just to split the rent.
Yeah, exactly. You get the isolation of private infrastructure with the economics of shared hosting. It fundamentally democratizes AI development inside a company.
That is huge. But I imagine once you democratize access, all those teams immediately want to connect their AI models to the company's actual databases, right?
Yeah, immediately. And the sources highlight a major update for that. The Java SDK for the Model Context Protocol, or MCP toolbox, specifically for databases.
Because getting an AI agent to reliably map natural language into a safe SQL query is notoriously difficult.
It's a massive headache. Yeah. But this toolbox provides a framework to connect AI agents to 42 different data sources. And it has deep support for GCP's flagship relational databases.
Which ones specifically?
So it supports Cloud SQL, which is their fully managed relational database service. It supports LODB. And crucially, it supports Spanner.
Right. Spanner is GCP's fully managed, globally distributed relational database, right? For the really massive workloads.
Exactly. So your AI can talk directly to all of them.
Okay, but hang on. We need to pause right here. Because we just built this architecture where multiple internal teams are sharing raw GPUs and their AI agents are talking directly to our most sensitive global databases.
Right.
If I am a hacker, my eyes just lit up. From a practitioner's perspective, this sounds like a security nightmare waiting to happen. How do we lock this down?
Yeah, that is the big question. And security really has to shift to an automated model here. So the nuggets detail some major updates to sensitive data protection, or SDP.
Okay, and SDP is the GCP service that discovers, classifies, and protects sensitive data, right?
Exactly. So SDP now uses AI-powered context classifiers and image object detectors. It functions as the core inspection engine for things like Model Armor and Security Command Center.
But why does the data need to be scanned by AI?
Because of how these models are tuned. Yeah. Let's say you take a massive unstructured data set like millions of customer chat logs, and you feed it into Vertex AI to tune your model.
Okay.
The model might accidentally memorize a customer's medical record or a credit card number, and once it's baked into the model, you can't just delete it.
Wow.
So SDP scans the raw data and redacts medical data, financial records, faces, ID cards, all of it, before it ever touches the Vertex AI training pipeline.
That makes a lot of sense. So that secures the data layer. But what about the application layer? Let's say I built a tool using Cloud Run.
Okay, so Cloud Run, just for context, is Google's serverless platform where you can run your code without managing any underlying servers.
Right. So if I have an internal tool on Cloud Run, how do I make sure only the right employees can access it?
So they just introduced direct integration between Cloud Run and IAP. the identity-aware proxy.
What does that change?
Well, previously, you had to manually configure complex application load balancers to enforce identity checks. Now, IAP sits directly on Cloud Run. It allows identity-based access control without all that manual load balancer configuration.
Oh, that saves so much time.
And it fully supports Workforce Identity Federation and CARS.
That is a huge quality of life update. But I want to tie this security conversation back to that 2025 Google Threat Intelligence report you mentioned earlier.
Yeah, the 90 zero-day vulnerabilities.
Right. With a massive 48% targeting enterprise tech, the report predicts that in 2026, AI will accelerate both the attackers finding vulnerabilities and the defenders using agentic solutions to patch them. Is this why Google Cloud acquired Wiz?
Absolutely. Wiz integrates continuous visibility across your code, your cloud, and your runtime. Google wants to combine that with their threat intel to support multi-cloud environments automatically.
Okay, but let me push back on this 2026 prediction for a second.
Sure.
If AI is speeding up the attackers and AI is speeding up the defenders, aren't we just entering an automated arms race?
Basically, yes.
I mean, what happens when our Gemini defensive AI is actively fighting a hacker's AI in real time? Doesn't the defense just shut down our own network in a panic?
Well, that's exactly why you need these dedicated specialized agents.
Yeah.
The AI isn't just wildly shutting things down. It's recognizing patterns and dynamically closing vulnerable ports or isolating containers while keeping the main app running. The human becomes the strategist, and the AI handles the real-time tactical fight.
Which means, to survive that kind of automated combat, the foundational plumbing of your cloud architecture has to be fast, private, and just super easy to maintain.
Exactly. And the foundational networking is evolving too. For instance, the Nuggets discuss a new reference architecture for private RAG networking.
RG meaning a retrieval augmented generation, where the AI searches your private docs.
Right. And this new architecture ensures strictly private connectivity. It uses a multi-project structure.
How does that work?
You have a routing project, a shared VPC host, which is your virtual private cloud, and then dedicated service projects for ingestion, serving, and your front end. The point is, the data never traverses the public internet.
Okay, so it's like a highly secure bank. The routing project is just the bank lobby.
Right.
But the serving service project, where the data actually lives, is the deep underground vault. The money or the data moves between the vaults safely without ever being carried out onto the public street, which would be the internet.
That's a great way to visualize it. And keeping all those vaults maintained is getting easier too, thanks to the general availability of unified maintenance.
What does that cover?
It's a central dashboard for planned maintenance across Compute Engine, which are GCP's customizable virtual machines, along with GKE, Cloud SQL, and even Looker.
And Looker is GCP's enterprise platform for business intelligence and data apps, right?
Exactly. And unified maintenance ties all of this directly into cloud logging for standardized alerts.
So it's all in one place. That's incredibly practical. What else is happening at the infrastructure level?
Well, GKE has a massive update for autoscaling. It now natively supports custom metrics in the Horizontal Pod Autoscaler, or HPA.
Okay, natively is the key word there. Why does that matter?
Because previously, if you wanted to scale based on, say, queue depth, you had to use external adapters or export your metrics to Stackdriver. It added latency and cost.
Ah, I see.
Now, you can scale directly based on pod signals. It saves money, reduces latency, and it's actually positioning GKE perfectly for telco operators who are modernizing their 5G core networks using AIOps.
Wow, 5G core networks. But what if you need even more raw power, like beyond what standard GKE nodes provide?
Then you look at the new H4D virtual machines. These are powered by 5th-gen AMD EPYC processors, and they are designed specifically for high-performance computing, or HPC.
What makes them so fast?
They use cloud RDMA via titanium network adapters and Falcon hardware transport.
Wait, RDMA remote direct memory access? Doesn't that mean the servers basically bypass the CPU and talk directly to each other's memory?
Exactly. It completely removes the traditional networking bottleneck. For molecular simulations, like running the GROMACS ES benchmark, these H4D VMs are 4 times faster than the previous C2D machines.
4 times faster.
Yeah, and 70% cheaper.
That is absurd. Okay, so we've talked about the models, we've covered the cost-saving GKE developer tools, the automated security, and now this insanely fast network foundation.
Right.
Let's actually see what happens when a major enterprise puts all these GCP puzzle pieces together to build something we use every day.
Yeah, the Nuggets highlight a fascinating proof of concept between the BMW Group and Google Cloud. They're working to automate workflows for in-vehicle voice commands using Vertex AI.
Okay, in a car.
Yes. But the pipeline is what's really interesting. They are moving from massive large models to optimized small language models, or SLMs.
Wait, I'm slightly confused. Small language models.
Yeah.
I mean, everyone in the industry right now is obsessed with massive scale, trillions of parameters. Why would BMW want to intentionally shrink an AI model down for a car?
Well, think about the practitioner reality. A car needs low latency, highly specific models. It needs to adjust the climate control or diagnose an engine issue instantly.
Right.
And it has to potentially do that without any internet connection. You don't need a massive model that can write poetry when you're driving through a tunnel.
Okay, that makes perfect sense. How do they actually shrink? The blog post said it wasn't exactly straightforward.
No, it's a very complex pipeline.
Yeah.
It utilizes compression techniques like low-rank adaptation or LoRa and direct policy optimization or DPO.
Right.
Then they distill all that knowledge into a student model, something like Google's Gemma.
And then there's a quantization step, right? Where they physically shrink the math so it can fit on the limited hardware of an emulated head unit in the dashboard.
Exactly. They rigorously evaluate it before deploying it. And to me, this perfectly synthesizes everything we've talked about today.
How so?
Well, AI is the shiny object, right? But actual success on Google Cloud platform really comes down to practitioner fundamentals.
Yeah, the nuts and bolts.
Exactly. It's about clever resource management, like GPU time sharing. It's about locking down your data with SDP and private networking, and using purpose-built infrastructure, like GKE or those H4D VMs, to make it all run smoothly.
It really is all about the fundamentals. And if you're listening to this and you have your own Google Cloud expertise to share, if you're deep in those fundamentals, you can actually become an author for the Google Cloud Medium publication.
Yeah, it's a great opportunity.
There's a form linked right in the newsletter to apply. But as we wrap up, I want to leave you with a thought based on that BMW example.
Okay.
We spend so much time talking about massive cloud infrastructure, right? Huge data centers, infinite compute. But what happens in a few years when every single device we own, from our Wi-Fi routers to our refrigerators, has its own customized, hyper-efficient small language model physically inside it?
Wow, yeah.
All of them operating locally but being coordinated by the cloud. Where will the cloud actually end and the physical world begin? It's definitely something to think about the next time you talk to your car.